The following program is brought to you by Caltech.
So it's a pleasure to introduce Marco Tantardini. As I mentioned this morning, Marco was part of the initial formulation of this whole proposal that we made to CAC. He introduced the concept to me and helped contact many of the people who are here. And he's really been entrepreneuring this activity as an independent. He's worked at the Planetary Society as a Planetary Society intern. Then he went up to Ames. I don't know what you were up at Ames, but I remember we worked him up at Ames for a couple of months, and he's gotten his master's in astrodynamics with missions to Lagrange points, and has been working on the whole issue of trajectories that go to the Lagrange points. And he's, in addition to that, he's an entrepreneur starting a business in jazz radio. But he's not going to talk about that now. He's going to talk about the low energy trajectories to Lagrange points.
Thank you, Lou. So good afternoon. This workshop is about moving a small asteroid, and as Lou mentioned this morning and as John mentioned this morning, we're going to consider a different destination. A previous study at JPL considered ISS as a potential final destination for this small asteroid. But from tomorrow on, we will discuss other destinations as Lagrange points. It could be Sun-Earth Lagrange points and Earth-Moon Lagrange points. And so during my presentation, I will give a definition for those of us that don't know what a Lagrange point is, of Lagrange points. Then I will talk about orbits, about these Lagrange points, and the invariant manifolds that are connected to orbits about these points, and that are the reason of these potential low energy trajectories. And then I will talk about why moving a small asteroid to a Lagrange point of the Earth-Moon system or of a Sun-Earth system. And we will have a brief overview of missions that have been sent from the Earth to Moon and Sun-Earth Lagrange points. And then I will discuss some ideas that we will discuss from tomorrow on about trying to match pure low thrust, as Damon discussed before, with these low energy trajectories. Because the idea is that if you use these low energy trajectories, you might need less energy to move the asteroid to the final destination. So you might need smaller SCP systems, or smaller solar panels to reach a final destination. So if you study the motion of a body about a central body, so like a spacecraft about the Earth or about the Sun, you won't see the Lagrange points. So a simple model to have a definition of what a Lagrange point is this so-called circular restricted free body problem, where you have a massless body that is moving in the field defined by two main bodies that are orbiting about their common center of mass. M1, for example, is the Sun, and M2 is the Earth. Or M1 is the Earth, and M2 is the Moon. And the third mass is massless in terms that its mass is much smaller than the mass of M1 or M2. And so these are the equation of motions, and the Jacobi constant is an integral of motion, and it gives you an idea of the energy level. And so, for example, here, if you look at where the third body can move for its energy level, you have the so-called surfaces of field that define the boundary for the emission motion of the third body in this field. So for a low energy level, high Jacobi constant, the third body, so for example, our asteroid, or a spacecraft can move about, let's say, the sun or about the Earth or outside here, or can move about the Earth, about the moon, or outside there. And these lines are zero velocity curves, so if a spheroid body is on this line, it has a zero velocity, and this is a forbidden region. So if you increase the energy level or you decrease the Jacobi constant, this area here, is going to collapse into a point, and this can be taken as a definition of L1, that is a point of equilibrium because you have zero velocity. And still, if you decrease the Jacobi constant, you will have a point here which is L2. If you keep decreasing, you have a point here which is in the position of a counter-Earth, for example, for a sun-Earth system. You have L3, and then you keep increasing the energy level, and you end up having this situation where the spacecraft or the asteroid can move anywhere in the space defined by the two main bodies. So for example here, if this is the sun and this is the Earth, these are the position of the Lagrange point. So L1 is in between the two main bodies, L2 is outside, and for example, in terms of distances, L1 and L2 are about 1.5 million kilometers from the Earth. So one astronomical unit is about 100 times the distance L1 to the Earth. And if this is the Earth and this is the Moon, the distance from the Moon to L1 is about 60,000 kilometers. As I said, we want to move a small asteroid. If we move it to a Lagrange point, it could become a potential destination for human exploration, and it's something that I will discuss later. But if you study the stability of these Lagrange points, the collinear ones are a point of unstable equilibrium, while these two are point of stable equilibrium. So if you put an object here, it will stay there, but a small perturbation will take it away from its position of equilibrium. But you can exploit the instability to have orbits that tend to this libration point, or even to orbits about the Lagrange point. So for example here, for the Sun-Jupiter system, the Jupiter is around here. This is the forbidden region for a given energy level, and this is an orbit about the L2 point of a Sun-Jupiter system. And so as you can see here, if your object is in this tube or in that tube, these trajectories tend to the orbit about this Lagrange point. So for example, for our asteroid return mission, if we manage to insert the asteroid into this tube, then it will go naturally into an orbit about the selected Lagrange point. This is due to the fact that in the circular restricted free body problem, the reference frame is rotating as the smaller primary. And so, for example, here, this system is rotating anti-clockwise. So an orbit here has a distance from the Sun which is smaller than the distance the distance of Jupiter from the Sun. So this is faster, so it will tend to the orbit here. This has a distance which is bigger, so it is lower, it will tend here. And the same here. This is smaller, so it's faster, it goes away. And this is bigger, so it's slower, and it goes away. So why moving an asteroid to a Lagrange point? Well, in terms of trajectory designs, there are three parts. There's a robotic mission where you launch a spacecraft from the Earth and you send it to an asteroid. Then we have to come up with a capture mechanism. And then there's a second leg where you move the asteroid to the final destination. And if you move it in a region that is appealing for a manned mission, then you can have a third mission design study, which is the trajectory design from the Earth to the asteroid. So if you study here, for example, a classical Hohmann transfer from LEO, from an orbit of about 400 kilometers from the Earth, to a Lagrange point, you will see that the delta V to launch from the Earth to arrive in L2, for example, of the Sun-Earth, or to L2 of the Earth-Moon, or to L2 of the Earth-Moon, the first delta V is about the same, so they want to leave the orbit about the Earth. But the delta V to stop in the Lagrange point, where we might put the small asteroid, is different. And for Sun-Earth L2, it is much smaller than for Earth-Moon L1 and L2. And so, for example, now at NASA, at least from as long as I know, it's what you can read also on papers and newspapers, the goal is to send humans to an asteroid by 2025, by 2030, and the mission should last not more than 6 months. And since we are going to such a long mission, there's a constraint of having a target asteroid that should be at least 50 meters big. And so far we have just found 3 asteroids which have even just few windows, so we can go to 2009 OS5 either in 2020 or in 2036, or to 1999 AEO10 in 2025, or to 2003 SM84 in 2046, which is pretty far in time, in 6 months. But if we manage to move a small asteroid, for example, to Sun-Earth L2, to go there, it takes about 40 days. And so, for the whole mission, it will take about 80 days respect to 180 days. And since it's put in Sun-Earth L2, you don't have constraints in terms of windows. You can go there whenever you want. And keeping the small asteroid into Sun-Earth L2 or into an orbit about it, in terms of station keeping, is very cheap. So if you manage to capture the asteroid and move it there, then keeping it there is pretty easy. So just to give an overview of missions that so far have been flown to liberation points, the first one was the International Sun-Earth Explorer 3 that was launched in 1978, and that might come back to Sun-Earth L1 in 2014 if we perform some sort of maneuver. In 1995, SOHO, Solar and Heliospheric Observatory, has been sent into an orbit about L1, as ACE, for example, is about Sun-Earth L1. But all these missions have been sent from the Earth to a liberation point. What we are trying to do is to move an object that is in deep space, it's in natural orbit, to a Lagrange point, which is something different. So, for example, this mission, Genesis, that was studied here at JPL and Caltech, was the very first mission that was completely designed using the so-called dynamical system theory. So here, in principle, here you were using the invariant manifolds I talked about a few slides ago. So here, the spacecraft was launched from the Earth, and it was inserted into a trajectory which was tending naturally into an orbit about Sun-Earth L1. And then, using this instability, the trajectory went into the unstable manifold that was passing about Sun-Earth L2, and it had an orbit that was colliding with the Earth, as this was a sample return. So in principle, to perform all these maneuvers, you didn't need any extra delta V. There were a bit of delta V just to perform some correction maneuvers. A mission to Sun-Earth L2 has been the Wilkinson microwave anisotropy probe, and there are others like Herschel and Planck to Sun-Earth L2, Wind and Grail are in Sun-Earth L1. China has just moved Chang'e 2 from an orbit about the Moon to Sun-Earth L2. Artemis is a mission from the Y2 spacecraft, and they are both in Earth-Moon L1 and L2. And the James Webb Space Telescope is planned to be launched into an orbit about Sun-Earth L2. So as I was saying, in terms of trajectory design, for the robotic mission to an asteroid, we can divide it into two parts. The leg from the Earth to the asteroid, and this is going to be studied and modeled and done, as Damon discussed earlier. But if we want to move the asteroid to a Lagrange point, then probably we could find a new way of moving it. So not just pure low thrust, but using these trajectories that tend naturally to the final destination. So here, for example, this is the Sun, and this is the Earth. This is in a system that rotates with the Earth about the Sun anti-clockwise. So these bodies are fixed, and so here I picked the orbit about Sun-Earth L2. I will zoom in a couple of slides. And so this is, for example, the stable manifold of an orbit about Sun-Earth L2. So if you manage to insert the asteroid in here, and you manage even to make it match the energy level of these trajectories, then the asteroid, so then you can turn off your low thrust, your propulsion system, and the asteroid will go naturally into your final destination. So per bounce, it takes 1 year for the Sun-Earth. So if you insert it here, then it takes 1 year. If you insert it there, it's 2 years, and there, 3 years. Well, this is the unstable manifold, but so what if an asteroid, for example, is in this area when it has a close approach? So for example, another idea to capture it through these corridors is to use the stable manifolds that departs from L1. Well, in terms of manned mission, I forgot to say that before. I think we prefer Sun-Earth L2 compared to Sun-Earth L1, because if you are in Sun-Earth L1, there's a problem of communications and even for solar storms. So Sun-Earth L2 could be a better place, I think. But you can even capture the small asteroid through this manifold to L1, and then you can just use the heteroclinic connection between an orbit about L1 and about L2 to move it naturally, just in a very efficient way in terms of energy. So this is a stable, then you get here, then with a small perturbation, you get into the unstable, into the stable, and you are about Sun-Earth L2. And for example, this is taken from the Artemis mission. So even here you can see that there are connections between orbit about, this is for the Earth-Moon case, but it's the same. So about an orbit about L1 to L2, you can very easily move from one to another one. And so we have just seen how the stable manifolds look like. And potential targets that we are looking for probably have, as even Don showed this morning, and Damon showed just before me, because I think he was picking this one, and 2009 BD, which is in a couple of slides. So the targets that we are looking for have a semi-major axis close to 1, eccentricity close to 0, and an inclination close to 0 as well. So, and the manifolds are here, are very, very close. So for example, here I just took September then 27, but in 2020, when we might launch a mission, to it be in 2020, 2025. So we will have to look to the phase respect to the Earth. But from the moment, we consider that at this date, we managed to capture the asteroid. So if we turn on then the low thrust, we could manage to insert this body, for example, 1991 VG, into the stable manifold, then we'll take it then naturally into the orbit about the Lagrange point. And probably, so if our target is a Sun-Earth liberation point, since it's more energy efficient than taking an asteroid into an Earth-Moon liberation point or into a smaller orbit about the Earth, we might have already few targets that could be moved with 40 kilowatts of power. And maybe matching with these low energy corridors, for a transfer time of 5 years, we might even need even a lower level of SCP. So, and it's something that we will discuss from tomorrow on, and I think we will come up with some results by the end of the week. And here you see other objects that could be moved using these low energy corridors. And so combining low thrust with invariant manifold has been already studied, but for a trajectory from the Earth to a Lagrange point, and especially for the Earth-Moon system. So studying how to insert an object, in this case an asteroid, through low thrust into the manifold from deep space to a Lagrange point is something that is new, but we can definitely do it. So here, for example, Mingotti in 2006 studied how to launch a spacecraft in an orbit about the Moon, and here he put it into an orbit about L2 of the Earth-Moon system. And well, you can even just perform, a human transfer, the burn here to stop. But what they did was, from a GTO, you had a thrust arc, and instead of using pure, just pure low thrust to go there, then you try to arrive in a position where you match the state of the manifold with a right energy level, and then here, so with the blue line is the thrust arc. Then you manage to reach the manifold, you turn off your engine, you have the right energy level, and so then naturally you go to the destination you were looking for. Of course, this technique takes more time, so instead of going to the Moon in 5 days, it takes a few months, but you save propellant. And for our case, if the asteroid is close to the Earth, so as I showed before, in 1 or 2 years, the manifold can take it back to the orbit about Sun Earth L2. So just to conclude, what is going to be discussed with Damon, with Nathan Strange, with Pedro Llanos, and others that will participate to this workshop from tomorrow morning. So an idea to move an asteroid to a Lagrange point is to try to look at a technique of matching low thrust with stable manifolds. And first we have to look to the Sun-Earth case, because if you put an object into a Sun-Earth libration point, then that is a gate even for the Earth-Moon system. So, and that has been studied even here at Caltech 10 years ago. So then if the object is in Sun-Earth libration point, then if you want to move it to Earth-Moon libration point, it's very straightforward. But as I showed before, probably for the manned mission potential, Sun-Earth L2 is more interesting, both because it will be a first step into deep space. It's even in terms of transfer time, something in between what is proposed now of 180 days, because it's 80 days to go and come back. And so if you manage to combine low thrust with invariant manifolds, we might find that we already have targets that can make it, that we can move, and maybe you might need, for a given target that you select, you might need a smaller SCP system, so you might have a smaller spacecraft, smaller panels, and a mission that could be simpler and cheaper. So thank you very much for listening.